All right, we're going to start looking at chapter 2, um, and we're going to look at descriptive statistics. And we're going to begin our mathematical program here, where we're going to take our definitions and describe them out. So we're first going to look at frequency distributions and their graphs, and then we're going to look at other graphs. A frequency distribution is a way of trying to find patterns in our data. So we'll want to sort our data into chunks. And this sorting process can really help us see if our data clusters. Now, not all data clusters, but if we have a lot of things that we have measured and we want to find out what the true value of the population we're looking at, or what the true measure of something is, if we're looking for that truth out of it, if it all clusters towards one area, that can tell us that area is the most likely true value. And so we'll do this by creating frequency histograms, frequency polygons, and relative frequency. And we'll see that these tools are going to be really fundamental for when we do inferential statistics, and they really link them in chapter 5 and chapter 6 to looking at our sample and then in being able to talk about our population. So we'll start here. This is very much descriptive statistics, but it links over to inferential statistics, and we're going to build some things in the background. But a lot of the wording and terminology and the things we use will definitely be the tools that we use when trying to get an estimate for our population. So frequency distribution is, and I hope I have the settings here. I hope you can see the mouse moving across as I point, but it's made of classes or intervals. Now, in the research I've done, and when we've been doing statistics, because of some of the software things we use, I also will use the word bins for classes or intervals. And I was always taught it was like a container, waste bin, or a bin that you put things in, and they're spaced out, and you put things into your bin. And you'll see when we go to construct these that there is a construction method that is like creating or putting things into a container. And the intervals have a frequency, or that's how many pieces of data fit within that bin. So in this case, we have classes of 1 and 5, 6 and 10, 11 and 15, 16 and 20, 21 and 25, and 26 to 30. Now notice the numbers do not overlap. They can't overlap, but they fill all the numbers between 1 and 30. And so what this is saying is the data we measured, there are 6 values that are between 11 and 15. And this is saying there are 5 values between 21 and 25. So it's a way of counting how much stuff, or how what the values are of our stuff, but in a little bit wider areas. And we'll visualize this rather quickly, and we'll see that we can get some information about it. So the lower number is going to be called the lower class limit, and lower, the left-hand number, and the right-hand number is the upper class limit, because 1 is the smallest value that can fit in this bin, and 5 is the largest value that can fit in this bin. And then the distance between each bin is called the class width. And so there's a distance of 5 between every position in this. So between the first and the second lower boundaries, there's a distance of 5, but everything has to be spaced by 5. And so the distance between 6 and 11 is 5. The difference between 11 and 16 is 5. And if we look at the upper boundaries, there's a distance of 5. Later on, when we construct the midpoint, the midpoints will be separated by 5. The class width is how the distance between any piece of data through our successive classes. And then in the difference between the maximum piece of data and the minimum piece of data is called the range. And in the table that's created, we actually can't see the range, but in our data, we can. And so what we want to do here to construct these is, I'm going to go over these rules and then we'll do an example to pull the rules out, is we want to decide on the number of classes. And that's usually between 5 and 20. And to be honest, there's a lot of stuff later on in statistics where we'll look at where we will find ways of trying to pick the number of classes. But this is more of the art form in statistics, is the number of classes you can increase and decrease to try to see patterns. And this is where software, if we plot our data in something like Excel and we can't see a pattern in it in a low number of classes, we put more classes in. And if our data gets too spread apart and looks spotty with a large number of bins, we put less number of classes in. So there's not a good method where I can say use this amount of classes given this amount of data. It really depends on the data set itself and what you're trying to see. And that's kind of why we're moving, and we'll use Excel a lot, or and other statisticians and people in big data use software to visualize their data. There is no solid rule to pick the number of classes, but there's a lot of information we can see when we get the class numbers right. What's nice is, because we're going to be learning what these things look like and what they mean, the textbook problems are going to tell you use 7 classes or use 5 classes. And when we get our own data, we'll be doing it in Excel, and if it doesn't look right, we can tell Excel to use some more classes. What we want to do then is find the class width, which is we determine the range of data and we divide the range by the number of classes and round up to the next convenient number. I'm going to go through these rules, and then I'm going to do an example here and we'll do all the calculations in. I really want to make a recommendation that in the textbook, Appendix D has most of the formulas and equations we'll be using, separated by chapter. And so when you're studying or doing the homework, it might be good to have printed out the Appendix D from the textbook, because you don't have to go back and forth. You don't have to use the show me the other feature in Pearson to find the equations. Also, some of the equations we do here are not simple formulae where we just plug in a number. Sometimes we'll have to add up a lot of things first. And we'll see that right away when we look at these frequency distributions, and I'll point it out. And we'll continue from there. And so this is our first calculation. We're going to determine the range of data, and then we're going to divide the range by the number of classes and round up to the next convenient number. And we always have to round up for finding the class width, because if we round down, we might not leave enough room for all of our data. So we're always going to round up for the class width. And so we'll turn this into a formula. In fact, let me come over here and show you the formula for this. There we go. Get my drawing board out. And so it says find the range. So the range of the data is the maximum data value minus the minimum data value. And then the class width is the range divided by the number of classes. And I think in Appendix D, the only equation it gives you is class width equals range over number of classes. And so we'll remember the range as being the distance between the smallest data value and the largest data value. And so we're going to use that. And of course, it didn't move over to my blackboard. There we go. You could hear me writing away, but the blackboard didn't come off. I apologize for that. So the range is equal to the max minus the min, and the class width is the range divided by the number of classes. And so this is the first equation we're going to use, and we'll see it in use as we get all our rules into play here. Right, let's go back to our rules here then to build a frequency distribution. Then we're going to find the class limits. And so we take the minimum data entry and we make that the lower limit of the first class. And because we've found the class width now, we can add the class width to each lower limit to build all the lower limits. And then we can do the same thing for the upper classes. And the nice thing is a lot of our calculations will just be repeating using the class width on a piece of our data. And then we're going to make a tally mark for each piece of data in our that in the bin or the class that data would fit in. And then we're going to count up all those tally marks, and we're going to say that's how frequent that range of data is. And so these five rules will make a frequency distribution. So I'm going to take the data we example in the textbook, but I'm going to work it out because sometimes reading these steps in the textbook can be a little hard. So what we're going to do here is we have the cell phone screen time for 30 US adults on a recent day. And so we're going to construct a frequency distribution that has 7 classes. So the text is giving us 7 classes. Here's our 30 pieces of data, which are the minutes in screen time, and we're going to want to build a frequency distribution from it. So I'm going to switch back to my Blackboard here, and I'm going to put all of our data together. So let me clear this and give ourselves some writing space here. And because I need to see the data, I'm going to rewrite the data down here. So bear with me as I rewrite the data. There's 30 pieces of data, so I'm going to write them all out, making sure that everything fits on the screen here. Yep, that's good. So, and again, this is the example in the text and also the example in the PowerPoint lectures. So, give me a second here. You'll hear me mumble as I write. I apologize for that. But writing down 30 pieces of data can take a bit. But then appreciate, if I were lecturing this in class, I would do the same thing here. 256, 290. Almost there. Isn't this exciting? Sorry, I have to tease. Sometimes in recording these, and I guess you could fast forward until you see me say we're done. Right? You've got a little scroll bar to go through. I don't have a scroll bar to go through the moments in life. So I'll just have to get them all there. Two more columns to go. I think it's 276. Yep. 168. Last column. All right, so we said there's 30 pieces of data, and so since this does seem to be a sample of adults, because it's not all adults, I'll say n equals 30. I'm going to use a lowercase n, and there's 30 pieces of data in our sample. Now, the first thing we want to find is the range. And again, this is following the rules. It's on page 40 of the textbook of constructing a frequency distribution, and also on the slides. But right now we're going to go through the process of creating a frequency distribution by hand. Get back to you here. So it's the maximum data value minus the minimum. So we have to find the max and min. So normally I go, okay, 200 is my smallest number. 155 is now my smallest number. And as I scan through, nothing is smaller than 155. So I'll make 155 as my min. So highlight that. And now I need to find my max. So 200 is my max, now 239, now 252, now 384, now 405. And nothing is bigger than 405. So 405 is my max. So my range then will be 405 minus 155. So 405 minus 155 is 250. And so we were told that we want the number of classes in the problem will be 7. So the class width is the range divided by the number of classes, or 250 divided by 7. So 7 goes into 25 3 times. That's 21, so 40, so it goes 5 times. Let's see. I should really pull my calculator out, but I'll do it on the side here. 7 goes into that 3, 21, 40, so that's 5, 35, 50, will be 7, so that's 49, 10 once. And we know we want to round up, so even though my decimal places are continuing to go, I already know that to round this up, because it's greater than 35, that I'm going to call my class width 36. And so rounding up is the thing that we always want to do. So we now have our class width, and we're going to want to generate our frequency distribution table from it. And so the steps say start with my lower limit and build all my lower limits using the class width, and then I do my upper limits. Sorry, I found my calculator, and I'm always double checking my math because I hate doing math. Yeah, 3.5714. Okay, so my rounding was approximate. But because we always have to round up, as soon as I have this first decimal place, I know it's going to go up to 36. So I'll start my frequency distribution table here. So I know I'm going to have 7 classes. So what I'm going to want to do is I'm going to have 1, 2, 3, 4, 5, 6, 7. Now your book doesn't do this, but this is not a bad way for me to keep track of all the spaces I need to fill in on this next step. So let me get some lines here. Try not to cut things off too much. That should contain everything in the table. And I'll put a header up here. And so here will be my classes. Again, this 1 through 7 is just for me to remember my space. If you look at the examples in the book, they don't use it. And so it says start with the minimum value here. And so all of the lower class limits are going to be separated by my class width. So I can add 36 to 155, which gives me 191. And now I can add 36 to 191, which gives me 227. I can add 36 to 227, and that gives me 263. I can add 36 to 263. That'll give me 299. I can add 36 to 299, and I get 335. And now my last lower limit, I add 36 to 35, and I get 371. And so now I have my lower limits. Now classes cannot overlap. So, and they have to be equally spaced. So I can't have a 191 here, but I know I can have a 190. So I drop this number by 1. Now, I can add 36 to each one, but the same thing's going to happen. I can drop each number by 1 here. So 226, 262, 298, 334, and 370. And now to get my last one, because I don't have a number to drop by 1 here, I'll add the 36 to this and get 406. And notice 406 is just one more than our max 405. If we had not rounded up, we would not have room for 405 in there, right? Because if we would round it down, each of these would have been off by like 0.7, and 7 times 7, this would have, if we would have taken 35 instead of 36, this would have ended up at around 399. And so some of these wouldn't have fit in. So we always need to round up to leave room. And now what we're going to do is we're going to make tally marks. So we're going to count where the data is. And what we do is we look at this piece of data, and we're going to work through each piece of data, and we figure out which class it is in. So 200 is between 191 and 226. So we put a tally mark in here, and we cross that out. And 239 is between 227 and 262. So I put a tally mark there. 159, it was our min, so it's in there. 252 is here. 384 is in our last. And again, I keep calling them bins. Realize I did a lot of work with these things in my research, and bins was just the word I used. Your book's using classes and class intervals or intervals. I will still slip into using bins. I apologize. I mean the same thing. 296 is here. And so what I'm doing is counting. This becomes a counting exercise of figuring how much our data is within these artificial little spaces I made. Now let's see, 303, 400. And so I'm getting an idea of where all my data is relative to each other. 241 here, 256 here, 315 here, 330 there, 317 here, 352 here, 266 here, 276 here, 345 here, 238 here, 306 here, 290 here, 271 here, 345 here, 312 there, 293 there, 195, 168, and 342. And so we've counted up how many pieces of data are within each little range. But even if we look at this, if you kind of turn this on its side, this has a shape that, starts out, dips down, and grows. And we can see, if I highlight this here, most of our data is within there. The bulk of our data is within here. And so if I'm trying to talk about some truth of the population, these values have more weight to them, more draw to them. And so something about the truth of what we're looking at of this sample can kind of be focused around this middle part. Or at least that's what we're hoping to say. And so we turn this into a frequency, which will get the variable letter f, by converting these tally marks to numbers. And then what we're going to do is we're going to do a quick check here. And this is one of the first odd formulas we're going to see. And your book will say the sum of the frequencies. And so we use the Greek capital sigma, or capital N, which is the S in Greek, for sum. And what this is saying mathematically is add up all of your F's. And so we'll get a lot of things we add up that'll tend to come in columns. And so if I add up this entire column, 3 plus 2 is 5, 5 plus 5 is 10, 10 plus 6 is 16, 16 plus 7 is 23, 23 plus 4 is 27, and 27 plus 3 is 30. But when we started this, we said there were 30 pieces of data. And this kind of has to match. Once I've done all my frequency here, this should account for every piece of data. So when I do the sum of all of my frequencies, it should give me the total number of pieces of data. And so this is what a frequency distribution is. It is the ability for us to really start getting a visualization of how our data clusters and where it clusters. And a lot of the statistics we're going to develop, the descriptive statistics and even inferential statistics, we'll talk about what it means to clump together. How can we measure how clumped together the data is, or how spread out the data is? But just by making this distribution, we get the ability to start seeing that. The tally marks alone give us an idea of the depth. And we'll see in section 2 of chapter 2, a lot of the graphs we make do the same thing. They give us quick visualizations. Now, when we go to talk about the classes, it's better to talk about the middle sometimes, not just the boundaries. So what I'm going to do is I'm going to replace these numbers that I used just to keep track that I knew I needed 7 of these things. I'm going to replace them with the midpoints. So we're going to talk about the middle, because the middle will have meaning also. As you'll see if you look ahead in the chapters, figuring out the midpoint of our data matters, and knowing the midpoint of our classes also matters. It's kind of where the average for what would be in the class would be. So we'll calculate the midpoints. Sorry, I'm just erasing these. I just used them because I knew I needed 7. And if I started writing them one by one, I might accidentally put 8 or stop at 6. So I just wanted to make sure where I was. And so a midpoint is calculated by, we take the lower interval limit, or the lower class limit. So the midpoint is the lower class limit plus the upper class limit, and we divide by 2. That looks like tupper, not upper. So we take the 155 plus the 190 and divide the answer by 2. So the midpoint, and I'm just going to abbreviate that as the midpoint 1 for my first class, is 155 plus 190 divided by 2. And 155 plus 190. Whoops. So I went and found my calculator, but then I typoed on it. So, and we put that into the calculator and we get 172.5. Now the examples in the textbook go on and add these two together, divide by 2, divide by 2, add these two together, divide by 2. I don't know, that's a lot more calculating than I like to do. But my class width was 36. So the distance between the midpoints is also going to be 36. So I don't need to add these together and divide by 2. Once I have the lower one here, I can add 36 to this, which is 208.5. I can add 36 to this, which is 244.5. I can add 36 to this, which is 280.5. I can add 6 to this, which is 316.5. And I can add 36 to this, which is 352.5. And I can add 36 to this, which is 388.5. And so these are my midpoints. And midpoints will help us when we do some of the graphing. And then the next thing we can have is the relative frequency. And this is the secret sauce, the relative frequency. This information is what we're going to be able to use to link descriptive statistics to inferential statistics. And so the formula for the relative frequency, is equal to the frequency divided by the number of pieces of data. So in this case, I have 3 divided by 30 pieces of data. I have 2 divided by 30 pieces of data. I have 5 divided by 30 pieces of data. And I have 6 divided by 30 pieces of data. 7 divided by 30 pieces of data. 4 divided by 30 pieces of data. And 3 divided by 30 pieces of data. All right, I'm going to do a little bit of moving here. Let me get a larger marker for a second. I'm going to move some of the equations around so I'm going to get rid of this midpoint so that I can do some additions here. This is just like in class when I get completely covered in my chalk or whiteboard marker as I erase things off. All right, and let me go back to the pen I was using, which I think was this one. Nope, that's too big. Still too big. Definitely got a big, let's see here. This is what happens when you scroll down a page. There we go. All right, if we sum across the relative frequencies, well, I'm going to leave these fractions like this. These fractions have the same denominator. So, 3/30ths plus 2/30. Well, with the same denominator, we add the numerator, so that's 5/30. And so I can come down and I can add the 3 to the 2 to the 5. If I do the sum of all the relative frequencies, well, that's 30 over 30, or 1. And the sum of all the relative frequencies will always be 1. And we're going to translate that in a second. But if I run to my calculator here, and I'm going to turn these into decimals, this is 0.1. And this is 0.66666 repeating, so we'll round that to 0.7. We'll use standard rounding here, not round up always. We'll just, because the next thing over was higher, we'll standardly round that. This is 0.16 repeating, so we'll round that up to 17. This is 0.2. This is 0.233 repeating, so we'll round that down to 0.23. This is 0.13 repeating, so we'll round that down to 3, and that's 0.1. Now I want to talk about number and how we talk about statistics and why relative frequency is important here. When we say a percent of something, so if something is 25%, when we mathematically go to work with that, we do 0.25. We can think of taking the percentage, and if I want to turn it into a decimal, I move over 2 decimal places to the right. And if I have a number like this and I want to turn it into a percentage, I move 2 to the left for 25%. And that's because percent, per means to divide, and cent is the Latin word for 100. And so this means 25 divided by 100, or 25 things out of every 100. And so percent was kind of an old language for talking about fractions. I find in a modern data world, more and more people are speaking like this. And a lot of times you'll see me, I'll do a problem here, and I'll see this, and I'll say, that's 10%, because I translate the decimal to 10%. In language, we like talking about percents. They have meanings, but when I need to go use this mathematically, this number is easier to use. And we can look at it. We can look at that use here. I'm going to scroll up a little bit. I'm going to try to keep the table on the screen so I have a little bit of room. So this was a sample of how much people were using their cell phones. And so the sample was only 30 people in the population. But if this sample was indicative of the entire population, and let's say there were 1,000 people in the population, and I wanted to know how many was of that 1,000 would be within this interval range, well, this is saying that the relative frequency is 0.2, or about 20% of the people are in this range. So if this sample is what the population is like, then I can multiply this by 0.2. And so 1,000 by 0.2 is 200. And I could expect, if my descriptive statistics of the sample does describe the population, if I had 1,000 people, I could expect 200 of them to fall within the range of spending 263 to 290 minutes of screen time on their phone a day. And that's really what we're going to do with this. We're going to take relative frequencies and we're going to look at how we can attach it to the population. Of course, we're going to have to develop other language to say how good of a guess it is. How reliable is this size of a sample for the population we're looking at? So the relative frequency is a really important linking pin for us. But for right now, it's also a good measure because we can talk about the percentage, right? Almost a quarter of our data, right, 0.23 or 23% is almost 25%. Really, really close to 25% is within this one bin. Now, the other type of frequency we have is cumulative frequency. And what cumulative frequency does is it asks the question of how much data has come up until I get to the end of the bin. So I'm starting up at the top and I come down, and so far I've only accounted for 3 pieces of data. When I move down to the next bin, I have the 3 pieces here. Right? I have these 3 pieces, and I have to add to it these 2. And so if I've made it this far through the data, I've had a total of 3 and 5. And so for the cumulative frequency, we take the first bin and put the number in, and then we continue to add the frequency. So now if I come down to here, the number of pieces of data that came before is 5 plus 5 is 10. So if I make it down here, that's 16. If I come down to here, 16 plus 7 is 23. If I make it down to here, 23 plus 4 is 27. And if I make it down to here, that's 30. And so the cumulative frequency talks about how much data comes before the end of the bin that you're in. And later in this chapter, we'll turn this into percentiles. And percentiles are something we might be familiar with in testing. You can talk, I'm in the 70th percentile. What that means is where my score stood, 70% of the people were lower than me, and 30% of the people were higher than me. And we can kind of see, right, if we look at 30 pieces of data, then the halfway point is at 15. And so halfway is somewhere around here. There's 15 pieces of data up above and 15 pieces of data down below. And so even though most of our stuff is here, half of our stuff, well, a little bit more than half of our stuff is up here. And so we can use cumulative frequency as a way of talking about our data. All right, I want to pause this graph, this video here, and then in the next video, I'm going to graph this, and we're going to make a histogram, and we're going to make a frequency polygon on it.